Hey Calc, we're going to tie up our study of derivatives, and that will include a couple topics, and the first one will be called Newton's method. Alright, what he wanted to do was find a way to approximate roots of equations, solutions. So if you have a function like that, this is a root, that is a root, that's a root. So it's sometimes called zeros and sometimes called root solutions, and that's what we're looking for, where the function crosses the x-axis. And he came up with a method that used tangent lines to approximate roots. Sometimes it's difficult to solve a given equation for the roots, so he added a method that could approximate the roots to any amount of accuracy. So, alright, so we're going to think of how to do that. So if you recall way back in our definition of derivatives, we had f prime of x. When we first learned it, it was a limit. That's the only way we knew for a while of how to find the derivative, was this limit, which could be drawn out. But we're going to go back and visit it. There was an alternative method, which we may not have used as much. And it looks like this. Hold on. Back. F prime at c equals the limit as x approaches c of f of x minus f of c over x minus c. And if you examine these, you'll see that when you're looking at the derivative, which is the slope of a tangent, this one will look at x here and change of x here and come up and get the difference here, and then divide by change of x. So we have a rise over the run situation of here the rise is f of x plus change in x minus f of x. So that's like change in y. Sorry, let me zoom in here. So for these very small change in x's, f of x plus change of x minus f of x is this part, and this part is just change in x. So this isn't change. This is not really right. We'll just say that this amount here is change of x. So we go out from x, change of x. So I don't want to talk about this in detail. It's just that this is the slope, and this change of x is going to go to 0, where it actually becomes a tangent line. Here, let's see what that would look like. So in a similar function, we would have x here and c here. So x is going to approach c. So this is f of x, this is f of c. I guess maybe we should have x on this side. Sorry, I should have thought this through. All right, f of x, f of c, this is x minus c, and this is f of x minus f of c. So again, we have rise over run. Here we have the slope, and as the limit as x approaches c, then this distance becomes minuscule and becomes a tangent line. So this is the same information. This is rise over run, this is rise over run, they are slopes. So this was called an alternative method of finding the alternative definition of a derivative, and I believe we did a couple, but we mostly used this one. So We're going to use this one to derive Newton's method. So assuming that that is true, kind of trying to remind you about it in a rather poor way. But let's start from here and let us just take away the limit. Hey, who needs it? So now we have f prime of c is approximately f of x minus f of c over x minus c. So we're making approximations here. We know we're not exact. Let's multiply both sides by x minus c. So that's approximately f of x minus f of c. So we're okay with that. Then let's add c to both sides, f of c to both sides. All right, and here we are going to stay. So I'm interested when f of x is 0. So because recall we're trying to find the solution. So what is f of x? That's the y value. It's always 0. It's read right here. So we're going to set this equal to 0 and put it on this side. So we're going to have 0 equals f prime at c times x minus c plus f of c. All right, just following one step leads to the other. So let's just put in this substitution because this will look more like what we're going to see. Remember the c value right here. Let's just call that x sub n. So we're going to just rename x. C is going to be x sub n. And then this x over here is going to be x sub n plus 1. You'll see why this makes it a little clearer to use. So I'm just going to make those substitutions, not changing anything, just renaming. So I'm going to get 0 equals f prime. C is now x sub n. And times, here we hit x, so I'm going to call that x sub n plus 1 minus x sub n plus f of c. So I'm going to have f of x, oops, come back, x sub, f of x sub n. All right, I made those substitutions. And now, to finish, I really want to know, this time, I want x sub n plus 1 by itself. So I'm trying to get this by itself. So to do that, I'm going to distribute, get rid of the parentheses. So I have 0 times f sub x, f prime of x sub n times x. So this is one thing, x sub n plus 1, and then distribute here. I get f prime of x sub n times, and that f prime is just to that, x sub n. And now I'm up to here. Up to here, plus f of x sub n. All right. Let's pull, since I'm solving for this, let's pull it to the other side. So I'm going to get negative f prime x sub n times x sub n plus 1. Just moving this over, leaving this over here. We really are going somewhere with this. All right, now, again, keeping my eye on the prize, I'm trying to solve for that. I get x sub n plus 1 equals. So I'm going to divide both sides by that. It'll be disappearing from here. And over here it will be appearing. Alright, so simplifying as I see, I am going to get, these will cancel in this term, leaving x sub n. But when I divide it by here, it doesn't, these are two terms, so I have to divide each by that. I shouldn't really cross that out at this point. Hopefully you can follow. I'm dividing this term by this. That's when it does cross out. When I divide this by this, it does not. Let me move this down. It'll be a little more clear. Alright, so x sub n plus 1, finally by itself on the left, equals just x sub n, and then this divided by that, and it is negative Alright, that's Newton's method, and it's actually a lot easier to use than it is to derive. So you'll see. Alright, so this sets up this x sub n plus 1 and this x sub n, like you do it once, and to find the next one you do it again, and each one is called an iteration. So let's put it into practice. Alright, I'll just do one and explain a little bit how this method works. I'll go back to the original, just a little theory. Say we're trying to find this root here. Well, first of all, we make a guess. And so, say we guess, I don't know, that. So that's my first guess, my x sub 1. What this method is doing, it's going up and grabbing f of x sub plus 1 and finding the tangent at that point. So, and where that tangent crosses here, it's the second guess. So I got to extend this graph down a little so you can see how it works the next time. So that's one iteration. Is that a little closer to the root than this is? It is. All right, so now this is my x sub 2, we'll call it. So now I find f of x sub 2, grab the f of x sub 2 and form a tangent line there. Whoa, look how close that one is. That tangent line does cut at or very close to the real solution. So you see each tangent line creates a better and better approximation of the root. So this is the algebra for that. Finding the tangent line and correcting and finding the 0 from that tangent line. So let me write it again. Alright, so the next guess or approximation equals the last approximation minus this expression. Alright, so let's do one. We'll take f of x equals x squared minus 2. And I'll go ahead and take the derivative. I see I'm going to need it. So f prime of x equals 2x. Alright, to follow this, we're going to find our first approximation. And it's going to be x sub n, which I come up with. I just make a guess. So I just guess, well, let's see what it looks like a little bit. At least a rough look. This is the smiler drop down to. So a good guess of where that crosses. I have no idea what these values are. I'll just guess 1. I'm not even sure if it's on this side or this side. I think it's on this side. Yeah, it is. So let my first guess be just a guess. So I'm going to guess my first one, x sub 1 equals 1. I need a starting point. You can always start at 0. And each approximation will improve. So x sub 2, I'm going to find by taking x sub 1. So this x sub n is the old guess. We're finding the new approximation by starting with the old approximation minus the valuation of the old approximation 1 in the function. So I'm going to put in the numerator, 1 will go into here. I get 1 squared minus 2. And then on the bottom, the old approximation is put in the derivative. So I get 2 times 1. So that ends up being, let's see, 1 minus a minus 1/2. So I get 1.5 or 3/2. All right, so that's my first approximation. Was a guess. The second one was calculated using Newton's method. I got 1.5. So that's 1.5. And let's see what this answer really is. I think we can do this one. Let's pretend that we don't need Newton's method. We're just going to find the answer to this. We get 0 equals x squared minus 2. Bring the 2 over. Take the square root. X equals the square root of 2, which is 1.41, something like that. All right, so we're getting pretty close even after at 1.4, we're at 1.5. So we don't even need Newton's method to solve this, but you're in training. So now these are called iterations. The next iteration, the third approximation, will take, see if I can keep that in the screen, the last approximation, 1.5, minus, in the numerator is 1.5 thrown into this equation. So I'm going to get 1.5 squared minus 2 on the top, and on the bottom I throw the old approximation into the derivative, which is 2 times 1.5. And when I did all that, I got 1.4167. So that is getting very close quickly. All right, you'll be trying some of these. It's pretty much plug and chug, and we'll get to that. I think I'll do on page 233, number 1 to 6. So you can remind me of that if I forget. Jot it down. All right, till we meet, and we will do those. Thanks a lot for your attention, and I'll see you tomorrow.